Hello, this is the luckiest maths teacher in the world. Today we're learning about binary, or binary as the Americans call it. So why would we learn this? So binary will not only give us a great introduction to powers of numbers, which is what we're going to be doing for the next couple of lessons, but binary is extremely important in the world. It's used in computer science. In fact, you can't really do computer science without binary. So, what actually is binary? Binary is a system of representing numbers. It's base 2, as opposed to base 10, which is what we use in everyday maths. So, before I explain what it actually is and what we're going to do with it, let's travel in the time machine back to year 7. So, in year 7 you would have learned about place value. So we use a base 10 system. So where does the word base come from? Well, if we have something like this, 4 to the power of 3, we call the number that's being raised to a power the base, and this superscript number here is the power or the exponent or the index. So I'm sure you all know that 4 to the power of 3 means 4 times 4 times 4. Okay? Great. So we use a base 10 system, and that means that our whole system is based on powers of 10. So what does that exactly mean? Well, let's just look at a few dots here that I'm going to draw now. So we need symbols to represent how many dots this is, right? Now, of course, you all know that this is 9 dots, because this symbol here represents this number of anything, whether it be dots, whether it be chocolates, whether it be the number of premierships the Broncos are going to win this decade. 9 has the same meaning, this symbol, right? So in base 10, to represent numbers of things, we use 10 different symbols. So the 10 symbols that we use are 0, 1, 2, and so on, all the way to 9. There are 10 of them, right? But of course, we might want to represent a bigger number than the number of dots there, because, you know, Brisbane's awesome. They're probably going to win more premierships than that in our lifetime. So let's say we add another dot here, right? Now we could represent this new number of dots with some random symbol. I don't know, something like this. Okay, that could stand for the number 10. And we could do that for 11, 12, so on. We could do that all the way to hundreds of million. But how bloody hard would it be to remember 100 million different symbols? We just couldn't do it. But we have developed the system, base 10, where we can represent any number using a combination of these 10 symbols. Now you know this. If I want to represent the number of black dots there's now 10, I represent it like this, 1, 0. So each of these numbers, 1 and 0, comes from this set here of numbers. So instead of writing a totally different symbol for 10, what we've done is we have moved over columns, and that's how we represent numbers. We put them into columns. So you know that the first one is ones or units. You will learn in this part of the course that that's 10 to the power of 0. 10 to the power of 0 is 1. Then the next column along, you know, is tens. And then the next column is hundreds. And then the next one is thousands. I'm sure, as I said, you know, 10 to the power of 0 is 1. I'm sure you all know that 10 to the power of 1 is 10. 10 to the power of 2 is 100. 10 to the power of 3 gives me thousands. So I'm going to represent, and I can represent any number by filling in these columns. I can write how many ones are in the number, how many tens, how many hundreds, how many thousands, and so on. And this way I only need to use the 10 symbols that I mentioned earlier. So if I want to represent, let's say, the number 4,320, I represent it like this. So this is saying there are 4 thousands, 3 hundreds, 2 tens, and there are no ones. Now you would know from year 7 we can write this in expanded form. 4,320 can be written as 4 thousands, which is 4 times 1,000, plus 3 hundreds, plus 2 tens, and I could write 0 ones, but I don't really need to, right? So that's expanded form. Okay, so now I've explained that. Well, what is binary? Well, in binary, it's actually pretty simple. Instead of having powers of 10 for our columns, we use powers of 2. So that's what I mean when I say binary is base 2. So for binary, we still arrange numbers in columns, but instead of having the column of 1s, 10s, and so on, well, we still have the 1s, but the next column is 2s, which is 2 to the power 1. So again, 2 to the power 0 is 1. You'll learn a bit more about that later. So the next column will be 2 to the power 2. How many 4s? And then the next column will be 2 to the power 3. 8, right? So we can represent any number using these columns. Now, in base 10, we use 10 different symbols. In binary, we only use 2 symbols, 0 or 1. So you don't say we have 2 2s, for example. Instead of saying that, you'd say we have 1 4. So it turns out that we can represent any number in base 10 uniquely in binary, and vice versa. Every number that's represented in binary can be represented uniquely in base 10. Okay, so let's look at having a conversion between them. So the first thing we're going to do is we're going to take a number in binary, in base 2, and we're going to convert that into base 10. Now, as I said, all the numbers in each of the column must be either 0 or 1. So let's say we have a number like this, 1101. Okay, so this is in base 2. We usually put a subscript 2 to let everybody know that this is a base 2, not a base 10 number. So I want to take 1101 in base 2 and I want to write that as a base 10 number. Okay, so the principle that we use is the one that I just used for expansion. I showed you how to write a number in expanded form using base 10. Now we're just going to do it with binary. So this number 1101, very simple. We have 1 in the 8s column, plus 1 in the 4s column. We have no 2s, we don't need to write that, and then we have 1 in the 1s column, and I could write that as 1 plus 1. All I need to do is figure out what this equals. So 8 plus 4 is 12, plus 1 is 13. So 1101 in base 2 is 13 in base 10. So just to make that very clear, 1101 in base 2 is the exact same number as 13 in base 10. Okay, see, that part of it is very easy. Now you always get the same numbers. So if I have, say, 1101, like I do here, there is only one base 10 number that it corresponds to. So there's a one-to-one correspondence between numbers in binary and numbers in base 10. So you don't have to worry about that. Okay, so that's the easy part. Now I'm going to show you the part that is slightly harder. So I'm going to give you a number in base 10 and we're going to have to convert it to binary. Now to do this, we need to know our powers of 2. So hopefully by the end of this lesson you'll be completely awesome with powers of 2. So again, 2 to the power 0 is 1. The next power of 2 is 2 to the power 1. Then 2 to the power 2, 2 to the power 3, and so on. Okay, so these will help us in a second for our question. Okay, so I'm going to go all the way up to 1024. Of course, I could keep going, but that's all we're going to need for the question here. So I've written powers of 2. Now I've written them, I started with the lowest on the right because that's how we organize our numbers. The last column, the lowest column with the lowest place value, that goes to the right. That is the rightmost column, okay? Now in this, we're not worried about decimal points. We're only talking about whole numbers here. We could go to decimals, but we won't this lesson. So the question I'm going to show you is, let's say I have 1000 in base 10, so that's 1000 as you know it, and I want to know how I can represent that in binary. Now again, there's a one-to-one correspondence. There is only one answer to this problem. I can't represent 1000 in different ways. So how I'm going to do this is I need to do the opposite of what I just did. I need to write 1000 as the sum of powers of 2. I need to write it as a whole heap of powers of 2 added together. The powers of 2 are the numbers up here. Now, I could write 1000 as, say, 3 times 256, which is 768, plus 128, plus 64 plus 32 plus 8. Now that's a true statement. 1,000 does equal 3 times 256 plus 128 plus 64 plus 32 plus 8. The problem is, though, I don't want to have this 3. I only want to use each power of 2 once. The reason is because when I come to put this in binary, I can only put a 1 or a 0 in each column. I can't put a 3 in the 256 column. So how I'm going to do this is I am going to take the highest power of 2 that is less than my number, 1,000. I'm going to subtract it. And then I'm going to get a new number. And then I'm going to do the same thing. Find the highest power of 2 that's lower than that. So the highest power of 2 that's lower than 1,000 is 512, as we see above in the list of powers of 2. So I'm going to do 1,000 minus 512. Now, you can use your calculator if you need. That just equals 488. So I want to get back to 0. So I'm going to take my new number, 488, and I'm going to subtract the highest power of 2 that's less than that. So that's 256. Okay, and that leaves me with 232, same thing, 232, next lowest power of 2 gives me 128, and I'm left with 104, and then 104, take away the next power of 2, and so on, so I get equals 40, and then I have 40 minus 32 gives me 8, and now look, I'm left with a power of 2, so I can just go 8 minus 8 equals 0, right? Okay, so what I've essentially found just here is that 1,000 equals 512 plus 256 plus 128 plus 64 plus 32 plus 8. I have used each power of 2 only once. So 1,000 equals exactly what I just found. So because it's 512 plus 256, I'm going to put a 1 in each of those columns. And then plus 128, a 1 goes in that column, and so on, like that. Okay? So I found 1,000. Well, it's got no 1,024s. Just like in base 10, we don't need to put 0 in front of numbers. It doesn't make a difference. So there's 512 plus 256 plus 128 plus 64 plus 32. Now there are no 16s, so I put a 0 there, and I put a 1 here. Now I need to make sure that I fill up all the columns to the rightmost column to 1s. So I had no 4s, no 2s, no 1s, so I write it like that. Okay, now that's very, very long number as we see. So 1,000 in base 10 is equal to, in base 2, 1, 1, 1, 1, 1, 0, 1, 0, 0, 0. Okay, they are the same number. Now I'm sure you've cotton on to the fact from this example that to represent numbers in base 10, I need fewer digits. So to represent 1,000 in base 10, I needed 4 digits. Here in base 2, I've actually used 10 digits. Now that is a bit of a trade-off. In base 2, it takes more digits. Each of these digits is called bits. So each 1 or 0 used to represent a number is called a bit, and they use that a lot in computer science. So I need more bits to represent a number in base 2 than in base 10. But the good part of binary is, again, that I'm only using 2 symbols, 0 and 1. So the computer doesn't need to remember 10 symbols as it did in base 10. Okay, so that's probably why binary is used, because you only need to use 0s and 1s. Now, the whole basis of computer science is built on binary, so I hope you've learned something here. Please ask if you have any questions. Other than that, this has been the luckiest maths teacher in the world. Have a great day.